All right, I'm going to share my screen. Today we're going to be working in an R script called Linear Regression Model Workflow. All right, so I'm in Data Course On as usual. So Data Course On, it's in Code Examples, and then Linear Regression Model Workflow.r. Put your hand up when you got that loaded. Make sure you're in your last name R project. Right. Now you'll see a couple new packages that we haven't used before. We've used Tidyverse, and last time I introduced you to Modeler. Okay. Today we're going to use ggally, Lindia, Skimmer, Patchwork, and Carrot with an ET. Okay. So once you get this loaded up here, go ahead and go over to Packages, Install, and get those. So ggally, Lin, Lindia, Skimmer, Patchwork, and Carrot. And I guess make sure you have Modeler also. Ensure that install dependencies is checked so you get everything that you need, that these packages need to work, and then go ahead and install those. I'll give you a minute or two to get that going. Okay, those of you without hands up, is it you don't have this script loaded, or?
So I got in at 1. I didn't catch what we were loading up.
Okay, it's in your data course, Code Examples, and then the script is Linear Regression Model Workflow.r. Anyone else having trouble finding that or knowing what's going on? Cody, do you need a hand of something?
No, I just got in a few minutes late. I think that I've got them all loaded.
Okay. While these are kind of installing, this may take a few minutes. So make sure you get those installing ggally, Lindia, Skimmer, Patchwork, Carrot, and Modeler. Okay. I'm going to cancel that for me. All right. While those are installing, let's have a chat. What is a statistical model?
Would it be a formula used to make predictions based on existing data?
Formula used to make predictions based on existing data. All right. Anyone have commentary on that? Agree, disagree?
I would agree with that.
You agree?
Me too. I think a lot of times it's shown in graphical form of some sort.
Mm-hmm. Can be. Doesn't have to be. What's a model train?
Sorry, can you ask that question one more time?
What's a model train?
Is it an expensive hobby?
It is. It's an expensive hobby. Tell me more about it.
Like model trains?
Yeah, model trains.
They're scale models, usually made out of die-cast metal, that people build elaborate tracks and cityscapes for their model trains to go around, and they watch them. My brother-in-law is really into it. So I don't understand the appeal, honestly, but whatever floats your boat.
What is the point of a model train?
Oh, man.
To imitate the real thing.
To simulate.
Your brother-in-law cannot actually have a full-scale passenger train in his living room.
That is true.
I'm guessing. Yeah. Okay.
Yeah.
The point of a model train is to try to simplify and approximate the real thing. Same thing with the statistical model. All right. The reason we call it a model. The idea is that we're trying to simplify and approximate what? Not a train, but what?
A set of data.
A set of data. Okay, yeah. F equals ma. What's that?
That is one of Newton's laws, one of acceleration. Force equals mass times acceleration.
Yeah, that is a model of force. Mass times acceleration. Okay. What's the equation mean? That's the mathematical representation of how acceleration and mass combine to create force. Okay. It is a mathematical simplified model of reality. Okay. It is not, in any case, actually true. It's an approximation. All right. It's a very useful approximation, but it definitely breaks down at a subatomic level, right? All models are wrong. All of them. But that doesn't mean they can't be useful. Okay, so your goal in analyzing any data set is to extract information about reality. You can't measure every individual bacterium in somebody's gut. Can't do it. Okay. You take a sample and you make statistical inference based on that. You make a model of reality that fits the data, and you try to apply that to extrapolate to more general circumstances. So that's what the modeling part of data analytics is all about, right? We've imported and cleaned our data, we've visualized it, we've got some ideas just from looking at our plots. And so now it's time to create a mathematical approximation of reality based on our data in an effort to learn something about it that we can apply outside of our data set. All right, I'm going to run these. That old shortcut is Control-Alt-B just to run everything before the cursor. Okay, so here we are. We're going to be checking out two of our old friendly data sets, MT cars and Iris. Okay. And I'm going to do MT cars pipe GG pairs. What's this pipe do again?
Makes the previous thing the first input for the next thing.
First input, the next thing. And so GG pairs is a new function that comes from our little friend here, ggli. So if I run that line, it's going to take a second because it's making a bunch of plots. It's taking our entire mtcars data set and pairing up every variable and making an appropriate plot for those two. So let's see what it looks like. All right. Well, that's a big old chart. Why did we do this? What's it showing us?
Is it showing us pretty much every single graph we could make all at once?
Yeah, kind of. It is kind of showing us. I mean, the number of graphs we could make is infinite, really, but like this is showing us a representative graph of miles per gallon against miles per gallon. Well, what's that? It is itself. So it's showing us a density plot of the miles per gallon. Miles per gallon versus number of cylinders. Okay, 8, 6, and 4. Here's the miles per gallon. You can see the scale down here, 10, 15, 20, 25, 30. So I'm seeing things with 4 cylinders have higher miles per gallon than things with 8. Right. So it is showing us all the possible pairings, and what's really nice is that it gives us a correlation value. So it gives us what's called a Pearson correlation by default, showing us the direction and how significant that is. So what we're looking at here is miles per gallon. Is it correlated with cylinders? Yes, strongly. The direction is negative. So what does that mean? The more cylinders you have, the lower your miles per gallon. Cool. So GG pairs is a neat little tool. We can also do a little filter first. So let's see here with iris. Iris, then filter where species is just Setosa, and then do GG pairs. So we'll have fewer plots this time. Okay. So we're just looking at Setosa, so that kind of simplifies things for us, but it's a nice little breakdown. It lets us get to know our data. So here's just species and sepal length. If we just wanted to look at those two, it shows us all the possible correlations between those two. So here's sepal length versus itself. That's just a density plot. Species. Huh, well, there's the same number of each of those 3 species. Great, so our design is balanced. Okay. Then we've got species versus sepal length, and then sepal length versus species this way. Neat. Okay, so we visualize stuff. Now it's time to build models. So if you remember, our formula is give it the model class. So essentially what kind of math is going to be going on. Then we tell it the data to use, and then we say our formula. How would I read this, the highlighted part, in English?
Sepal length as a function of sepal width.
As a function of sepal width. All right, so our response is sepal length. This model is presuming that sepal width has some influence on sepal length. Okay, so I'm going to save that as mod 1. LM is linear model. And then mod 2. How would I read this one? Anyone? Did I cut out here? Help me out.
Yeah, the video is having trouble. That's why I'm hesitating in responding.
Oh, I can hear you. Sorry.
Okay, but you can hear me. All right. So sepal length as a function of sepal width plus species.
Change that plus to an and I like it
And?
better. Yeah.
Plus is an and.
Yeah.
Spooky.
All right. So here we go. We're saying that sepal length of our iris species is a function of, it's affected by sepal width and species. In other words, we're saying that there are two predictor variables that might influence sepal length. Okay. When I switch it to this third model, mod 3 here, I've changed the plus to a times. And if you remember from last time, that means that we're also going to be looking at the interaction. And so I would actually read this as sepal length as a function of sepal width and species and the interaction between sepal width and species. Okay. So we've got 3 models right there. Why did we make 3? Why not just 1? This goes back to what a model is.
Is it so we can determine the best one by looking at different ways they interact?
Yeah, I mean, we don't know what reality is. We're trying to build a mathematical model of reality based on some data we collected. Okay. I mean, think about like just epistemologically the hubris of this. We're going to try to approximate some aspect of the universe just by looking at 32 cars. Okay. It will be wrong, but it might be useful. But we don't know what the best model of reality is going to be based on our data. All right. So we're going to try a few different things. Okay. So in here we've got 150 little samples of iris flowers that we looked at, and we're convinced, for whatever scientific reason, that sepal length is affected by sepal width and possibly by species. So we're going to try out some of these. The most complex model in this case is mod 3, because it's actually got 3 terms. It's got sepal length, or sepal width, and species, and the interaction between them. Okay. So our models are getting progressively more complicated here. Let's take a look at the summaries. So summary of mod 1. How do we interpret this? Who wants to take a stab at it? What are the residuals? Has it been too long?
The residuals, aren't they like the difference between the equation and the actual points if you draw it through? Like you subtract one from the other and then you end up squaring it or something too?
Yep. It's because we did a linear model, and so we did a best fit line. That line has an equation. This is the difference between reality and our line. Okay. So that's just a summary of the differences. Okay. What are the coefficients?
It appears to have, if you can hear me because it's frozen again, appears to have a y-intercept. So that's, I assume, what intercept is. Standard errors, is that the same as standard deviation?
Yeah, think of it that way for now. Yeah. It's the spread. Yeah. T-value. So we did a t-test. And then what's...
And the last one's probability, I think.
It is probability that the response we got is greater than the absolute value of our t given a null hypothesis, and that's less than 2 to the negative 16th. So very, very tiny number. All right, so it's saying that that's significant. All right, what's this line? What is the second coefficient?
Are those all for the x value in what would be our linear equation?
The sepal length is our kind of y value, because that's our dependent variable. And we
Right.
said this is mod 1, and so sepal width would be plotted on the x. This is the effect of sepal width on the slope of that line. So maybe I should plot this. Seems like either I'm cutting out or something's getting lost in translation here, and you've forgotten over the long fall break what we did last time. So let's take a look here. ggplot, iris, aesthetics, x equals sepal width, y equals sepal length, plus geom smooth, method equals lm, plus geom point. Okay, that is our model visualized. Here it is mathematically. What is the slope of that line?
Negative 0.2234.
Negative 0.2234. What is the y-intercept?
6.526.
Bingo. All right. So our coefficients in a linear model are showing us what went into our line and the effect of sepal width on that. So in other words, what this is saying is that the average sepal length, the average y value, is 6.52. However, sepal width, for each increase of 1 in sepal width, you can expect to reduce that value by 0.2234. So as we go up from 3 to 4 inches in sepal width, or centimeters, we can expect to go down our average by a little bit, by 0.22. Okay, so that's the summary of our model right there. Okay, let's take a look at the output right here at the bottom. What does r squared refer to?
R squared is a measure of how closely the best fit line fits the data.
Yeah. Okay. And what's our final p-value here?
Looks like 0.1519, which would not be significant, right?
Yeah, I'm gonna go with not significant also. It's arbitrary, but the rule of thumb cutoff in biology is 0.05. If it's smaller than that, we say significant, for better or worse. I don't want to get too into the epistemology of what p-values actually are, but that's not significant. If you look at this, that's basically like saying we're not sure that this line is actually sloped at 0.22. It could be a flat line, right? Our data do not disprove the null hypothesis that this is a flat line and that sepal width has no influence on sepal length. Okay. If you kind of look at the gray area there, that's our standard error. Okay. It's our standard error here. It's showing the range of places that line could be. with some degree of confidence within our 95% confidence. And so a horizontal line could fit in there just fine. So that's to be expected. So our model tells us what overall about our hypothesis? We just did a statistical test.
This linear model might not fit.
It does fit. I mean, we made it fit. That's the thing, is we told it, hey, linear model, here's data. I need you to fit it. Here's the formula for your line. It fits it. This is the formula. That's the result that we got.
Well, like it might not be an accurate representation of the data. It might not be a good model.
Or what it's actually telling us is that it can't determine if sepal width actually is important for sepal length. It's basically saying, probably not. So it is an accurate representation of our data, actually. It can't be inaccurate because we fit this to the actual data set. That is literally the slope of the best fit line for sepal width versus sepal length. That is our only possible approximation of reality given this equation, this formula right here. Does that make sense? In a grander scheme, maybe we just didn't sample enough different irises or whatever. But from the ones that we did sample, it looks to be that sepal width has no influence on sepal length. And that's what our model tells us. And congratulations, you're done. Except what?
Except we have another model we could try.
We sure do, right? This first model is kind of stupid, given that we know that different species have different traits. Okay, so let's look at model 2, summary mod 2. All right, what do we get there? If I were to plot that,
Would it have put all three of them on one graph if you hadn't done the facet wrap?
yeah, you could. I did the facet wrap to just really split it out to make it a little easier to see. Here's our overall data. So let's see here. And here's our data split up. Oop. The data points are going to be the same. There's always going to be a sample that has exactly 3 of sepal width and whatever that is, 4.2 sepal length. We're going to see that again right here. There's 3 and our 4 point whatever. But now we're looking at it a bit differently. What's changed?
You've done the linear analysis or the regression analysis based on species itself. So each species has its own line.
We let the y-intercept change based on species. Okay. So in this case, species not considered here, y-intercept can vary based on species. Okay, so let's look at our output here. Here's our formula, sepal length as a function of sepal width and species. Okay. Here's our residuals. Here's our intercept. Previously, I believe, yeah, it was 6.5. Now, this model of reality is telling us that the average is 2.2, but that's going to change based on a few things. As sepal width goes up, you can expect the sepal length to go up as well. That's the opposite of our previous model, right? Here, we had a negative slope. Here, we've got a positive slope, somewhat steep. Okay. Then it says, if you are species versicolor, you can expect to add on 1.4587 to whatever sepal width and the intercept told you should be. If you're species virginica, you can add on 1.94. All right, what is unclear about that? Because that's going to be pretty important moving forward, how to interpret this. Let's see, if I were to predict the sepal length, I would say sepal length equals, and I'm just writing like a made up kind of equation here for you. Sepal length equals 2.2514 plus 0.8036 times sepal width plus 1.4587. So sepal length of versicolor. Do you see where this equation came from in this model? If not, please let me know. Let me clear it up for you. What about for Setosa, species Setosa? What would the equation be?
It'd just be the 2.514 plus the 0.8036 times sepal width without the last value on there.
Yeah,
right?
Absolutely. And you can see that actually makes sense in our plot here. Setosa is significantly and consistently smaller in sepal length than versicolor and virginica. All right. So our model is saying that we need to add a little bit to our y-intercept. We'll keep the same slope, okay, but we'll add a bit more. Okay. Now our third model, we're going to let the y-intercept and slope vary based on species. Okay. So, oh, I forgot here. Sepal width, that's significantly important. Versicolor is significantly different from Setosa, and so is virginica. Okay. Our overall p-value for this model is very tiny, so that's significant. Our R squared, this explains about 73% of the scatter in our data.
So that PR, that all of them have their individual PR value. Are those individual p-values?
These are individual p-values for each term in the model, yes.
Okay. And then the
This lets you know which parts of your model were explanatory and which ones were kind of unnecessary.
Okay.
So yeah, here it's saying that sepal width, the probability that the t-value we saw is greater than the absolute t-value, right? So this is just looking up your t-value in your table if you do this by hand, or it's a t-test. It's basically saying there's low chance that we would see this result if your null hypothesis was true, and so we're going to reject the null, and we're going to say that sepal width probably seems to be important. so does being species versicolor, and so does being species virginica. Now, overall, our model can be significant or not. And here it's saying that this one is. Our previous one, no, right? Our little slightly downsloping stupid line did not do a good job of explaining our data. This one does a pretty good job of explaining our data. Now our third model, we've got our intercept. It's changed a little bit. It's 2.63 now instead of 2.25. Sepal width, there's our estimate of the slope. And here is species versicolor, species virginica, but those are not significant. And then here are the interactions. The interaction of sepal width and versicolor, the interaction of sepal width and virginica. Essentially what that's saying is that the slopes of these lines aren't actually significantly different from each other. Okay. All right, our R-squared value, this model explains about 73% of the scatter in our overall data. So, 28% of where the dots are, it's still left to other variables to explain, and just random error and stuff like that. All right, so we've got our three models. We kind of look at them, look at our outputs, see which ones are significant, look at the R-squared value. How much does this model explain? Okay. And so I'm going to show you the next steps. We want to look at our models a bit more closely and see if they're actually a good mathematical fit. So that's where this package here, Lindia, comes in. It gives us this fun little function called ggdiagnose. And you just give it a model. All right. Who has seen any of these sorts of plots before? See a couple hands. All right. Nobody wants to say anything. I'm going to make you then. Somebody tell me what histogram of residuals is showing us.
Mine just appeared, but that would
Oh.
be related to the distance from the line.
Uh-huh. It's showing the distribution of how distant things are from the line, okay? So it kind of looks like a little bell curve almost in this case. We don't have very many things that are super distant. More often than not, they're within one. Okay. What about residuals versus sepal width? The sepal width is our x-axis, our predictor in this model.
Let's see. It looks like it's kind of showing where, like, whether the positive or negative at a certain point on sepal width.
Yeah, okay, so imagine this plot had like really big residuals on the left side and very small residuals on the right side. What would that be telling you? Is that our model was good at capturing the effect of sepal width when it was really big, but when sepal width is small, it couldn't capture the effect very efficiently. It didn't explain very much. Right. The reason we look at charts like these is to see if our model is doing a decent job of capturing reality. Okay. for the residual versus sepal width plot here, you want that to just be random noise, like a big shotgun blast. You don't want to see any pattern in there. We do okay here. Okay. Things like Cook's distance, this kind of helps you find outliers that might be important. There's a bunch of stuff in here. If you've actually gone through the reading and done the R for Data Science chapters, you have seen these and you know how to interpret them. If you haven't, then it's all brand new to you, and that's why you're feeling lost. Okay. Now, we're going to do that for each of our plots, or each of our models here. Take a look at them. They all seem to be doing okay. This one's taking species into account, and so we've got residuals versus species. So it did a fairly even job for each one of those species. That's good to know. And then for model 3, let's see. Yeah, it's doing a good job too. Okay, so each of these models is doing okay mathematically. So let's pick one. Which model do you want to go with? Mod 1, 2, or 3?
3.
Why?
It seemed, I'm going back through mine, it seemed a little tighter than the others, I guess, for lack of better terms.
Multiple R squared. So we've got, let's look at adjusted R squared. That's kind of corrected for some stuff. 0.718. And then for model 2, adjusted R squared, 0.7203. So actually mod 2 is a little bit tighter than
Tight.
mod 3. What's that?
It's tight.
It is. Is Model 2 actually different from Model 3? Do they do a different enough job distinguishing from each other? That's where this little term comes in. So often we'll make like 2 to 5 different models that we think might explain reality. We'll check them all out, kind of see how they're doing, look at their R squared values, and then we can actually compare to see if they're different. And that's, I know this is confusing, but ANOVA in lowercase, it's how you compare 2 models to see if they're different. So I'm going to say ANOVA mod 1, mod 2. Yes, they are different. They do a different job of explaining the data. All right, ANOVA mod 1, mod 3. Yes, those are different. All right, ANOVA mod 2, mod 3. No. They do a similar enough job explaining the data that we can't tell them apart.
Usual.
What's that?
I don't know what's going on with in and out.
Oh, okay. So this ANOVA command helps us determine whether it's worth even having 2 different versions of a model. If we can't tell them apart, they're functionally equivalent. They do an equal job of explaining a reality according to our data. So we've got mod 2 and mod 3 that are essentially the same. Okay, one doesn't do a better job of explaining our data set than the other does. So we can pick between them. However, mod 1 is definitely different from mod 2 and from mod 3. So if you remember, one of the ways we can see if a model is fitting reality is basically just see how far the points are from the best fit lines. Okay. What did I do there with these 3 lines of code?
You're just looking at the average residual of each model, right?
Yep. So I squared all the residuals so that there's no negative positive conflicts. Okay. Took the average, called it mod 1 mean squared error, mod 2 mean squared error, mod 3 mean squared error, and then stuck on these all on one line. The little semicolon just says new command. Okay. So I put them all on one line for convenience, and it pops them out. Which model is best?
It's
Model
the same
3.
tie, more or less. They're really close.
There's a slight difference between models 2 and 3, and it looks like model 3 has a smaller mean squared error. But I think you're about right in that they're pretty close. I would almost call that a tie. Okay. What else do we remember about model 2 and 3? ANOVA can't tell them apart. Neither one does a significantly better job at explaining the data than the other, but we know that either one of them is better than model 1, right? So that's basically saying that model 1 didn't take species into account, so it's doing a piss poor job of explaining reality. Species are important. Model 2 and model 3 took species into account, just let the math play a bit different in how the slopes were calculated. But it really didn't seem to matter how we treated our slopes. Species was overwhelmingly more important than that. Okay. So we can pick between these, and kind of a rule of thumb, you want the simplest model that does a good job explaining your data. I don't know if that makes sense or not. I'm going to try justifying to you why I'm picking model 2 over model 3.
Because it's simpler.
Yeah, even though this little number right here is a tiny bit smaller than this one, it's much simpler. Model 2 is, okay? And models are supposed to be simple. It's supposed to be an easy mathematical representation of reality. All right. So if you remember, we did this function called add predictions last time, where you give it a data set and the model. Okay. It basically goes in and calculates where all the points would be on that best fit line. Okay. So it's giving you the model's prediction. And by default, it's just going to add a new little column to your data set called pred. Okay. So we were trying to figure out sepal length based on sepal width, and our model didn't take species into account. And so pred, it's predicting a sepal length of 5.74. Well, we got 5.1. Okay. It's not horrible. The difference between those two values is our residual. Okay. Pred minus sepal length. That's it. Okay. Then this pred minus that actual sepal length. That's what the residuals are. Now the gather predictions function lets us feed it several models, and it spits it out for us in a nice tidy format. I'm going to call that DF. Okay. So if I look at DF, it gave us two new columns. One of them is called model, and one of them is called pred. So model, look, mod 1, there's our predictions. Mod 2, there's our predictions. So this is a nice, long, tidy data set where model is a variable, so it gets its own column. So we can look at all three of our models. All right. Let's see here. That's model 1 by itself. So those are the predictions that were made based just on sepal width without taking into account species. And there's how far reality was from it. Okay. If we draw little dotted lines, you can see how the residuals are actually calculated. It's the literal distance from the predicted point to what we actually saw for each one of those. Okay. And now here, we're looking at all three of our models and their predictions. All right. Is it painfully clear to you how bad Model 1 is? If not, please let me know. Or not just how bad, but why it's so bad. I think that's probably pretty important. Why did it do such a crappy job at reflecting reality?
Because since it's not looking at each species individually, it's grouping them all together. And when you group them all together, there's too much, I guess, variation between sepal width and sepal length for it to put together anything meaningful.
Yeah. Setosa is so much lower than the others. It's just smaller flowers, okay? That it's drawing down that best fit line, okay? So your model is basically thinking that as sepal width gets bigger, sepal length drops. But that's just because Setosa has really short, stubby, wide flowers, right? It's got greater width overall than these others. It's still going up within that species. The wider the flower, the longer it is for the sepals. Same thing for the other two species, but when you don't include that in your model doesn't know about it. Okay. This is an important lesson. Models are very, very stupid. Like totally unintelligent, unaware of what's happening in reality. This mathematical formula does not know that different species have different features. How could it? It's just a mathematical formula. You have to tell it that it does in order for it to know that, okay? If we trained our little model here and said sepal length as a function of sepal width, it will give you an answer. It absolutely will. It did. We got an answer way back up here, summary mod 1, and our answer was what? Does sepal width affect sepal length?
You got an answer that was just not significant.
Yeah, it said no. It said no. Sepal width is not important for explaining sepal length. So it gave us an answer. It's perfectly happy to give you an answer when in reality we know from seeing these other models and just knowing something about these species that sepal width is strongly correlated with sepal length. It just depends on the species. Okay, so what's the lesson in here? The moral of this story that I'm trying to hammer in?
Don't take your p-values for granted.
Sure.
Also, you got to try quite a few models to see that your data, I guess what your results are, is going to be accurate.
Yeah, try a few models, know something about your system going into it. You know, a physicist who's never taken a biology class should not be making models of iris sepal length because he might not know that sepal width is important or that species are a thing, right? Not to pick on physicists. Know something about your system ahead of time, right? Do your background research. Think about what's reasonable and what's not. And most importantly, I want you to be aware that R is perfectly happy to let you make a stupid model and give you an answer. This is mathematically correct, right here. According to this model, sepal width doesn't have any effect on sepal length, okay? Because we asked the wrong question. So be aware of that. You can make models all day long that tell you absolute bullshit garbage about reality that's not useful for your system, okay? If you don't know anything about the system you're studying, you won't pick that up. You would come away from this saying sepal width is not correlated with sepal length, okay? Now, we throw in a measurement of species and suddenly we see, oh, it's very strongly correlated. Okay, it just depends on the species. So within each species, there's a correlation. All right, so be aware of that. And that's why we try things like making several models and kind of looking at our data. Okay. Of course, if you went in and did a ggplot and colored by species, you would see this correlation, right? It kind of shows you that automatically. Be ready to translate your ggplot into this kind of model notation, right? This sepal width plus species. Okay.
Question.
Can we?
Yes.
Oh yeah, him first. He can go first.
Is there a package that does that for you, that translates your ggplot into a model?
No.
Or vice versa?
No. There are packages that will help. Let's see here. So there's the Broom package. It gives you a function called tidy, mod1. So instead of giving you your model results in this kind of hard to copy paste format, it gives it to you as a data frame, so you can easily extract different parts of it. So I can do that and get my actual p-values. Okay, so that kind of helps. But there is not a package that will automatically do it because there is no one scenario that could be right every time. Does that make sense? You actually have to know about how your model was calculated, and you have to know what's going on in that plot in order to do this correctly. It's kind of hard to see in this example, but the slopes of the lines in Mod 3 are different from the ones in Mod 2. It's actually just here in Setosa. It's like a little bit shallower of a slope. You can see when you compare the little points here. So looking at these, I think you ought to be able to say sepal length is a function of sepal width plus species. You should be able to see that in that plot. Okay. I don't think that's unreasonable of me. Matter of fact, if you don't get to the point where you can see that in a plot and translate it to a little model, you're not going to do super well in the rest of this course, because we're going to be making models and testing them a lot. Okay. The remainder, what we'll do on Wednesday, is this notion of cross-validation. Okay. So this was really developed by statisticians and data scientists, where you don't want to use all of your data to train your model. You just want to use some of it and then test your model against some random data it hasn't seen. We'll get into that next time. So there's a bit more to this. Let's take a look at some plots here. Okay, so we're just looking at, again, our predictions. So here's doing the exact same thing with MT cars. Again, the difference between a plus and a times. In a plus, for a linear model, they all have the same slope. In times, the slopes are allowed to vary. Okay. And that's where we'll pick up next time, is cross-validation. But questions about today? The second time I've walked you through models, so hopefully it's starting to stick. You really need to get yourself onto the resources I put online and go through those 2 chapters. Walking through it, they use some fake generated data to really illustrate how these models are built, and they kind of start getting into the fact that all the statistical tests you've ever done in a stats class, t-test, one-way ANOVA, two-way ANOVA, those are all actually linear regressions. So for the most part, we'll be doing linear regressions in this class. Okay. Questions?
Can we look at
yeah.
the table for the summary of Model 2 again?
Table for Model 2. Summary Mod 2. Okay, what about it?
All right, so it should have 3 different y-intercepts on it, right? One for each, or
yeah.
One for each species.
What it does, since species was a factor, it takes the first level that it finds and sets that as the standard to compare the other levels against. So the intercept here is the setosa. So let's plot it. Yeah, this will work. Okay, so mod 2, here's setosa. It's basically saying that the intercept is 2.54, but we're going to add 0.8 to that for every 1 point of sepal width that we have. Okay. And then if you happen to be species versicolor, go ahead and add an extra 1.4587. But if you happen to be species virginica, go ahead and add an extra 1.9468. Did that help clear it up? It's not it's not showing this. Yeah, this is the slope for the effect of sepal width on the slope is right there. Yep. So for each increase in sepal width of 1, you can expect an increase of 0.8 in your sepal length. Now the intercept, this is kind of confusing because it only shows species versicolor and species virginica. This right here is the baseline for species setosa, and we're just going to add for these. And that should make sense to you. Here's setosa. They've all got the same slope of 0.8036. Okay. But if you're versicolor, you're going to add 1.45. Okay. If you're virginica, you're going to add 1.94. So it's just those 3 little points right there. This one, that one, and that one. That is 1.4587 bigger. That one's 1.9468 bigger than that.
Okay, and then Model 3 did give the separate slope. Gotcha.
Now in Mod 2, they all have the same slope. Mod 3, they all get a separate slope. And it gets much more confusing to look at. Okay. So translating this into an equation is a bit tougher. Okay. We've got our intercept here. We've got the effect of sepal width. That's significant. And then we've got our effect of versicolor, effect of virginica, and then the effect of an interaction. And so we have to actually add an interaction term into our little model of this. Okay. When using R to do data analysis, you don't really need to get hung up on how to write the formula or write the equation for each point, because we just have that add predictions function, right? Add predictions, in the back end is going to calculate based on everything the model knows and based on the data set, going to calculate the exact predicted outcome for that set of predictor variables. So that's why they never bothered trying to write the super complicated code for deriving the actual equation from this. It's because you don't need it. It's already stored in your model. Okay. So far, we've only learned the one type of model, though, this linear model. Right? We're going to stick with it this week, and next week kind of branch out into other types. Models that aren't straight lines, for example. Still got a few minutes left for any clarifications I can help offer.
I have a question.
Yeah.
I've just been following along with you. Everything's working great until if you go down just a tad there. I think it's the thing right below that. Yeah, where that ggplot is. When I run that, it gives me an error. It says you're passing a function as a global data. And then it says, have you misspelled the data argument in ggplot? Do you know why that might
This
come up?
one right here?
At all? Yeah.
Okay. That's because you didn't run this line.
Oh, something up there I missed. Okay.
Where we assigned df to be
yeah.
this gathered predictions.
Okay, I totally missed those lines.
Yep. So today's lesson came at you kind of fast. I moved a bit faster since we already saw this, but I realize it's been a few days because of, fall break and your brain shut off. I need you absolutely to spend time practicing this, going through this script, going through the modeling intro, modeling basics, modeling fitting here in week 9. Go through those resources, and then we've got some practice scripts here that I want you to look at. Okay, this is the one we'll get to on Wednesday. These two you should be ready to do. All right. It's a lot, but it is the meat and potatoes of data analysis, right? This is where we're doing statistics. We're testing our hypothesis here. A pretty picture is nice, but you got to do your stats or else it's not believable. You could just be seeing patterns, all right? This is really important stuff. I need you to practice that and be ready to roll, okay? After this, we're going to move into more complex models, okay? And then we're basically done. We did our little loop. It's time to communicate results, so we'll look at making a reproducible report. At that point, we are working on our final projects for the last month, probably the last like 5 or 6 weeks of this class. Okay. So we're going to be packing in a lot of knowledge here in the next 2 to 3 weeks. In the meantime, keep practicing and keep thinking about what data analysis project you want to do. What kind of models do you want to generate? What plots do you want to see? Okay. We're getting close. You may not feel it, but you're almost a data scientist. You're almost like ready to go for it. Yeah. All right. Well, if nobody has anything, okay, yeah.
I do have one last question. Where are the due dates actually on the website? Because there was a thing where it said the due dates are on the website, but I could never find them.
They're on Canvas. For which?
Oh, they're
Due
on
dates.
Canvas? I swear it said it was on the website. So
due dates for what?
Just exams. Like I didn't actually know when exam 2 was due, but I did it. When was that due? I already did it, but.
Oh, it's due this Friday.
Oh, because I did it yesterday. I had no clue when the due date was, so I kind of panicked and did it as soon as I saw it. That just popped up on me.
It's on Canvas also. Yeah. the due date there.
Yeah, I never see it on the to-do list though. Is it in a list or something, or inside a document?
It might not show up in your to-do list because there's nothing to turn in for it on Canvas, right? It's just
Wait,
like a
Good
placeholder,
point.
Did you just say that the exam's due on Friday?
right?
Um.
When did you say it was?
The entire class, I'm pretty sure, was under the assumption that it was due yesterday.
Yeah, I was under that assumption as well.
Yeah, I got it done yesterday by 9:30, which is
I thought you said you were going to do a Git poll at 9:30 a.m. today.
I
And
did
that-
a Git poll at about 10 o'clock today.
For
I had
example,
that in my calendar. I saw that in my calendar. It said do a Git poll, so I did.
we were all under the assumption that that was for exam 2.
I
Okay.
have also had just kind of a general hard time with
Right.
due dates and finding those. So if you could point me in the direction of where I could find all of
We
them.
talked about this in class, right? Am I just forgetting when we said it was going to be due? Yeah, I see exam 2.
Maybe.
It would have been great to have a few extra days.
No, you already had like a week and a half on it.
Oh, there you go. Your boy.
Here's what's happened. I messed up. I didn't ever have it due this Friday. It was due before class this week, and my fall break brain broke down. So let's check it. Exam 2. No content. That's nice. Whatever. Did everyone get it done?
Not everyone.
Oh. We can raise our hands, but I did.
I did too. So.
Who did not get it done? How about that? Just yell at me. So everyone did get it done? Let's check here. Find dot type directory name exam 2. So looks like Eads, Josh, and he's not in the call today. Is that it? Okay. Well, I'll be forgiving on that. It's okay. And it wasn't a hard exam, was it?
Question
Part
4
of
was
it.
hard.
Yeah, 4 was pretty tricky.
Yeah, okay. But overall, it's really just making some plots, doing a bit of cleaning. You should be at the point where that's getting to be pretty quick for you. That comes with practice, okay? And more than practice, repetition. So go ahead and retake the exam, even though you already know the answers. Do it again, over and over, and it'll become a lot faster. Your third exam is going to be modeling, okay? And so you'll be reading in data, cleaning it, visualizing it, and modeling it. So we're kind of building on this. And then your fourth exam is your final, which is redo any previous exam that you don't like the score on. Oh, I'm not trying to be too much of a stickler with due dates or whatever this semester. Time is a flat circle. Nothing matters anymore, so it's fine. If you're a day or two late, I'm not gonna trip out. Don't worry about it. But if you haven't got the exam done, get it done ASAP so I can get them graded. More than me getting them graded, I need you to be at the point where you're comfortable doing that exam before we move on into the more complex modeling.
Thank you.
Yeah. Well, we are officially out of time. I'll hang out for a couple minutes if anyone has lingering questions, but otherwise, you are free to get out of here and go practice your R.
Great. Thank you.